In the Primer Fields Part 1, it was shown how two magnetic bowls of opposite magnetic polarity would form a variety of plasma structures within a vacuum chamber. The color and shape of these plasma structures were clearly determined by the following factors: the shape of the magnetic bowls, the spacing and orientation of the magnetic bowls, the type of purging gas that was used, the vacuum level within the vacuum chamber, the electrical voltage used, the polarity of the direct current electricity used in the experiment, and the positioning of the electrodes within the vacuum chamber. All of these factors influence the shape of the plasma formations within the vacuum chamber. In the Primer Fields Part 1, the plasma formations were often shown starting out with long arcs that gradually transitioned into a stable formation. This startup transition was due to a change in the vacuum level alone. Once the vacuum level is stabilized at the correct level for the plasma formation desired, the light emitted by the glowing plasma can be turned off and on instantly. So the electricity is not responsible for the fields that form the plasma formations. The electrical polarity determines how the plasma conforms to the fields, but the fields are not at all formed by the electricity. A reversal of the electrical current that causes the plasma to glow will cause an entirely different pattern to be revealed in the vacuum chamber, but this is due to a simple polarization change in the plasma, which reveals a different aspect of the same field structure. The electrical polarity is not causing the fields to change, it is just changing how the plasma responds to the fields. Here we see the instantaneous effects of this electrical polarity reversal, as the DC electrical supply is switched between polarity states, just as you would flip a light switch on and off. In the Primer Fields Part 1, it was shown how these opposing bowl-shaped magnetic field emitters control the formations of both steel and magnetic balls around the magnetic bowls. It was also shown how 5mm steel balls formed geometric patterns in the nucleus area between the two magnetic bowls. We also saw that these steel balls repelled each other because of the magnetic field that was induced into each of them in the nucleus area. The magnetic bowls also induce magnetic fields into ordinary steel balls both inside the bowls and around the bowls. The induced magnetic fields then cause the steel balls to all repel each other, and at the same time the fields of the magnetic bowls confine the steel balls into organized rings and patterns. It is very clear that these magnetic bowl-shaped fields impart order into the matter around them, whether in the vacuum chamber or outside the vacuum chamber. It was also shown how one of these magnetic bowls would induce a magnetic field into an ordinary steel ball, which then caused the steel ball to be repelled away from the bottom of the bowl. Then, by utilizing what we learned in the laboratory experiments, we were then able to come to understand the structures we find in space better than ever before. We discovered that we could now show how galaxies, stars, nebula, and most all other structures that we find in space could be explained without requiring black holes, dark matter, or dark energy. That brings us to part 2 in the Primer Field series. To begin with, we are going to explore the magnetic substructures that are found within these magnetic poles. The reason for the glowing rings that we see inside the magnetic poles in the vacuum chamber will be explained in this section of the Primer Fields. Understanding the function of these rings is critical to understanding how fusion works in the stars. It will also be shown how the bubbles inside the magnetic poles are caused by magnetic confinement, and how these magnetic bubbles are related to the ejection jets that are emitted from the top of these bubbles. This animation shows a magnetic bowl. In the bottom of the bowl, we find 3 magnetic substructures. Now we will slice the bowl in order to get a better view of these magnetic substructures. I have named these magnetic substructures the confinement dome, the flip ring, and the choke ring. A regular compass is much too large to properly map the fields within the magnetic poles, so a much smaller magnetic compass was fabricated to map the fields in and around the magnetic poles. The red and blue arrows shown here indicate magnetic orientation and the direction of the flow of matter in and around the magnetic pole. The red arrows indicate magnetic north, and the blue arrows indicate magnetic south. Here we see a magnetic sphere being used to reveal the shape of the confinement dome. Here we see a string of magnets being used to show the magnetic field lines in and around the magnetic pole. Here we see an example of the ejection forces that exist within the magnetic bowls. Then we see that this ejection force can be extremely strong. So just as we see in the plasma experiments in the vacuum chamber, we see that these ejection jets start at the top of the confinement dome and shoot out of the bowl in line with the axis of the bowl. Then when we take this knowledge and apply it to the Vela pulsar, we find some incredible validation of this theory. Notice how perfectly the bowl shape, flip ring, and ejection jets all match with the structure of the Vela pulsar. Once more, we see a magnetic sphere being used to reveal the shape of the confinement dome in the bottom of the magnetic bowl. The only way for the magnetic sphere to get under the confinement dome is for it to enter at the flip ring at the base of the confinement dome. Once under the confinement dome, the magnetic sphere is trapped under the confinement dome. If the magnetic sphere is forced above the confinement dome, we see that it is ejected up and then once again held above the confinement dome by the magnetic forces within the bowl. Now we have an animation showing how magnetic matter would react inside of the magnetic bowl. For now, we will be focusing on the function of the flip ring. The red and blue balls are labeled to indicate north and south magnetic polarity, red for magnetic north and blue for magnetic south. So as you can see, all the particles within the magnetic bowl are drawn to the flip ring, where they then enter the area under the confinement dome. Notice how at the flip ring the balls flip magnetic orientation. That is why I call it the flip ring, because it flips the magnetic orientation of the matter passing through it. This animation shows how particles of matter flow inside these magnetic bowls. The particles of matter entering the bowl are each induced with a magnetic field of their own. Then these particles of matter are drawn down to the flip ring, where they violently flip magnetic orientation and then become trapped under the confinement dome and above the choke ring. This flow of matter continues until the supply of available matter is exhausted. These bowl-shaped magnetic fields act as matter compressors. They will compress available matter until there is nothing left. That is why there is a vacuum in space. Most all of the available matter has been compressed so that all that remains in space is a vacuum. Now we will take a look at the function of the choke ring. Shown here are steel balls that are held in place at the choke ring. The balls are free to rotate around the choke ring, but they resist exiting out the bottom of the bowl or going back up into the bowl. The flow of matter is choked at the choke ring, which is why I call it the choke ring. The choke ring in the bottom of the blue bowl, or the south magnetic bowl, functions exactly the same, except the magnetic polarity of the choke matter is reversed. So here in the bottom of this bowl in the vacuum chamber, the glowing ring is the flip ring. In this view, we see how the flow of plasma is choked down as it goes through the hole in the bottom of the bowl. This is the choke ring at work, confining the plasma magnetically into a narrow stream. Now we are going to take a look at another magnetic substructure that exists below the bottom of the magnetic bowl. I refer to this area as the flip point. The flip point is in line with the axis of the bowl. Here we see the microcompass being used to show how the flip point flips the magnetic orientation of matter at the flip point. Past the flip point, matter is held away from the bottom of the bowl, but inside the flip point, matter is drawn into the bottom of the bowl. In this demonstration, notice that the steel ball is pulled towards the flip point and then held at the flip point by the interaction of the magnetic fields of the bowl and the induced magnetic field of the steel ball. This flip point repulsion is the reason we see the ejection of matter from the bottom of the Vela pulsar. In January of 2013, the Chandra X-ray Observatory released this series of images showing the flow of matter around and into the Vela pulsar. As you can clearly see, the matter is ejected out the top and out of the bottom of the Vela pulsar. Most of the matter coming out of the bottom of the Vela pulsar then moves up towards the top of the Vela pulsar's magnetic bowl, where it flows back down to the flip ring in the Vela pulsar. You can even see the evidence of the confinement dome above the flip ring in the bottom of the Vela pulsar's magnetic bowl. Despite what we have been told, the pulsation of the Vela pulsar is not due to a rapidly rotating neutron star. That is just what was theorized before the discovery of bowl-shaped magnetic fields. In a bowl-shaped magnetic field, the confinement dome is constantly trying to confine all the matter beneath it. But when the energy of this confined matter becomes too great, some of this confined energy escapes. Located at the top of the confinement dome is its weakest point, and this is where the confined energy escapes. In other words, this point in the confinement dome acts as a relief valve. If you Google relief valve chatter, you will see that relief valves can come to a point where they will release pressure in very rapid pulses. In other words, the relief valves will oscillate. Since the confinement dome is acting as a relief valve, it can come to a state where it is rapidly pulsing as it releases a burst of energy and then closes again, cutting the flow of energy being released. Since the confinement dome is operating as an electromagnetic relief valve, it can release these bursts of energy at very high frequencies. So pulses of energy can be rapidly released and then stopped immediately by this action of the confinement dome. This is why some pulsars exhibit these rapid pulses of energy that can suddenly stop and then restart hours or even days later. If we look at how these bowl-shaped magnetic fields function in the vacuum chamber, we see that they also emit energy in rapid pulses. In the ejection jet of HH-111, we can see very definite pulses in the matter ejected. By comparing the jet of HH-111 with a jet that is externally electrically driven in the vacuum chamber, we see that they have dramatically different structures. HH-30 is another example of bowl-shaped magnetic fields with the ejection jets in line with the axis of HH-30. The externally electrically driven plasma jet, as shown in the lower image, is very steady and it fades gradually, whereas the jet of HH-111 has dramatic pulse formations and a sudden cutoff at the tip. The structure we see in the jet of HH-111 does not fit with what would be found in an externally electrically driven plasma jet. So I must conclude that the jet of HH-111 is not externally electrically driven. This same logic would apply to the jet of M87. This jet is not a continuous structure that would be expected if this was truly externally electrically driven, as the jet on the right is. But we do see the common overall shape of the jets due to the shared magnetic bowl structure responsible for the jets in both M87 and the jets in the vacuum chamber. As we examine the Crab pulsar, we see that it is also easily explained with a bowl-shaped magnetic field. Here we can see the knot-like pulses that are emitted by the magnetic bowls in the vacuum chamber. Also notice how the plasma is choked down by the choke ring as it flows up into the upper bowl. You can find a lot more information out about pulsars on my Facebook page. This includes a very interesting study on pulsars that was released in January of 2013. This study brings further validation to the theories of pulsar behavior presented in the Primer fields. Now we are going to look at supernova remnants. Supernova remnants are all that are left of a star after it explodes or goes supernova. Astrophysicists believe that all of these bubble-type supernova remnants once had a star in the middle of them. Then they believe that the bubble we see is a shell of gas moving away from where the exploding star once was. But I am now going to show you that this concept is incorrect. So we need another explanation for what formed these bubble-type supernova remnants. Occam's razor is accepted in science as a way to determine which solution to a problem is most likely the correct one. The goal when using Occam's razor is to provide the simplest solution possible. Therefore, in line with Occam's razor, I'm going to show you a very simple explanation of the forces behind bubble-type supernova remnants. The solution you are about to see would apply to all bubble-type supernova remnants, as well as many other bubbles that are observed in space. As you may have expected, the solution is found in bowl-shaped magnetic fields. So here again we see the confinement dome, the flip ring, and the choke ring. Particles of matter are drawn down into the magnetic bowl and down to the flip ring. The particles of matter flip magnetic orientation at the flip ring and then become trapped under the confinement dome. As the matter continues to accumulate under the confinement dome, it causes the confinement dome to swell in size. In other words, the bubble is continually growing. This is why when they measure these bubble-type supernova remnants, they are found to be expanding. Notice the lip at the bottom of Tycho's supernova remnant. This is where the flip ring is located. Then we have supernova remnant SN 1006. Notice the appearance of the top of this bubble. Notice the axial formation up through the middle of this supernova remnant. There are times when the internal pressure of the bubble is too great and the magnetic bubble will fail at its weakest point. The choke ring may also allow some matter to escape out of the bottom of the bowl. This is exactly what we find in the Jellyfish Nebula. Scientists have studied supernova remnants with a wide variety of instruments. When you carefully check all this data, you will find that it all conforms to the theories of supernova remnant formation presented in the Primer fields. One of the most thoroughly studied supernova remnants is SN 1006. This image of SN 1006 shows what is seen in wavelengths of light visible to the human eye. Now added to the Hubble image, we have that which is seen in other wavelengths by other telescopes. Where the magnetic field is the strongest is at the choke ring, and this is also where matter is compressed to the greatest density. This is why the choke ring area of SN 1006 is the only part of SN 1006 visible to the human eye. This is where matter has the highest density and becomes visible. Notice that other images of SN1006 and other wavelengths also conform to the structure that would be expected within a bubble formed by a bowl-shaped magnetic field. Here we see the flow of matter going down to the flip ring, and the ejection of matter out of the top and out of the bottom of SN1006. Notice that this matches the flows that we saw earlier in the Vela pulsar. Then we have this very interesting supernova remnant. I will just let the images do the talking. Then as we observe the Ring Nebula, we also see that it too is actually formed by a bowl-shaped magnetic field. So based on what we now know about how bubbles are truly formed in space, the massive bubble structures that have been discovered in our own Milky Way galaxy make complete sense. Then we have this new study that I just received this morning, which also confirms the theories presented in the Primer fields. The magnetic nature of our universe is undeniable. The formation of Eta Carinae is no longer the mystery that it once was. The Eskimo Nebula is also easy to understand once you realize that it too is formed by bowl-shaped magnetic fields. Notice the bubbles inside of the nebula referred to as M29. So now that you know the patterns to look for, you will see that there are many confirmations of the Primmerfield's theories found throughout the universe. In this image of CMIS 147, we see the flip ring, the choke ring, and we can see the matter ejected out of the top of CMIS 147 at less than escape velocity, and therefore the ejected matter is drawn back down to the flip ring of CMIS 147. In this image of the Rosette and Cone Nebula, we can find 3 magnetic bowls with bubbles in the bottom of them. There is one bowl on the right, one faint bowl in the middle, and of course the large bowl with the bubble in the bottom that we see here. The bubble nebula is clearly in the bottom of a bowl. Then active galaxy NGC 4438 is shown here with the bubble that it contains. By now you don't even need me to show you the bowl-shaped magnetic fields that form the infamous Hourglass Nebula. You can even see the confinement dome down inside the Hourglass Nebula. So let's review the basic structure inside these bowl-shaped magnetic fields. The red bowl represents north magnetic orientation, and the blue bowl represents south magnetic orientation. The shape of the magnetic substructures within the red and blue bowls is identical, except they are of opposite magnetic orientation. In stars, the 2 bowls would be at the poles of the star, and the flip point would be the focal point, or the nucleus, of the star. In the Primer Fields Part 5, we will look at how these fields function in the Sun, including why the Sun flips magnetic polarity every 11 years and the true reason behind the solar cycle. Notice that in the vacuum chamber experiments, you can see that there is a brighter inner magnetic bubble in the middle of the outer magnetic bubble. In other words, there is a bubble within a bubble. In NGC 3918, we also see a bubble within a bubble. Then the Cat's Eye Nebula also has a bubble inside of a bubble formation that cannot be explained by the currently accepted theories. But when we apply the Primer Fields approach, you will see that these bubble-in-bubble structures are very easy to explain. So as you can clearly see, all of these bubble in a bubble type formations are very easy to understand once you actually know the real truth. There are also rings observed in space, and here you can see how these rings can be formed between two bowl-shaped magnetic fields. Then we see again how the Red Square Nebula could be formed between two bowl-shaped magnetic fields. Now we are going to take a look at how these bowl-shaped magnetic fields are responsible for what has been discovered in and around Saturn. Saturn's rings are so pronounced because the rotational axis and the magnetic axis of Saturn are exactly aligned with each other. Saturn is the only planet in our solar system with this exact alignment, and that is why rings are not as defined around other planets as they are on Saturn. The rings around Saturn are held in place by the bowl-shaped magnetic fields, just as the disk of plasma is in the vacuum chamber experiments. The spokes that appear in the rings of Saturn have long been a mystery, but when you apply what we learned in the vacuum chamber experiments, the cause of these spokes become very clear. Notice that these spokes are at a tangent to the surface of Saturn. Notice how the burst of plasma emissions from the center of the vacuum chamber are also at a tangent to the rapidly rotating core in the vacuum chamber. When we overlay the vacuum chamber video with the images of Saturn and its rings, the solution to the source of the spokes in Saturn's rings becomes obvious. Then we can see that the Primer fields theories also clearly show the true reason behind the polar auroras on Saturn. Shown here is the basic magnetic field structure that exists around Saturn. Then this image of Saturn's North Pole captured the interest of the whole world. But it's not really that difficult to explain once you understand the theories and concepts presented in the Primer fields. If you look closely, you will even see the magnetic bubble in the middle of this image. Then, of course, we have the intriguing hexagonal pattern seen in the pole of Saturn. Around the axis of these bowl-shaped magnetic fields, we find that these fields will cause matter to form these regular polygonal shapes. In the ring of steel balls around the nucleus in this image, we also see this polygonal effect. So as you can see, most all of the mysteries of Saturn are very easy to explain when you apply the theories that you have learned in the Primer fields. Now let's take a look at Jupiter. Here we see that Jupiter's magnetic axis and rotational axis are not quite aligned, and that is why the rings of Jupiter are not as pronounced as the rings around Saturn. Notice the appearance of the polar areas of Jupiter. This image from NASA reveals the ring formations around Jupiter. These views of the poles of Jupiter reveal very organized patterns about its axis. Next to the red asterisks, notice the dark spots on Jupiter as they rotate by. Now notice these same type of flows on the bowls in the vacuum chamber. You can see the fingers of plasma on the lower bowl in this image. Then with the larger bowls, we also see the same type of pattern next to the glowing sphere. So by applying the theories presented in the Primer Field series, we can see that we now have a very logical explanation for the patterns that we observe on the surface of Jupiter. That brings us to the end of the Primer Fields Part 2. In this installment, we learned about the magnetic substructures that are found within the bowl-shaped magnetic fields. You learned about how ejection jets truly function. You were shown clear proof of bowl-shaped magnetic fields at work in the Vela pulsar. The forces at work in bubble-type supernova remnants were also revealed. We also saw that bubble-in-bubble type nebula are easily explained using the theories presented in the Primer Fields. Then we ended with a brief discussion of the forces at work in and around Saturn and Jupiter. In the Primer Fields Part 3, we will be exploring the wave-particle nature of matter. This will include an in-depth examination of light and the reason it exhibits the dual nature that we find in the infamous double-slit experiment.